This graphic illustrates the three important concepts related to electricity. Current is measured in amps or amperes. Current is the rate at which charge flows through a circuit. Voltage, the voltage provided by the voltage source drives the current through the wire, and the resistance, measured in ohms, is the reduction in current that is caused by the electron collisions inside the circuit. In this presentation, we are going to use the resistance equation to solve problems. What is the resistance of a 0.3 meter length of copper wire that has a cross-sectional area of 5 times 10 to the negative 5 meters squared? You can find the resistivity of copper in a chart on page 4 of your reference table. Now we have everything we need to find the resistance and just need to put everything we have into the equation. Here is the substitution with units and the answer with units. Make sure when you divide by that number on the bottom that is in scientific notation, you use parentheses in the beginning and parentheses at the end. So how could you alter the dimensions of this wire to reduce the resistance? The fact that both the resistance and the length are in the numerator of the equation tells us the relationship between these two variables is direct. This means if we reduce the length of the wire, we will reduce the resistance too. Think about it. If an electron moves through a shorter path, it will reduce the number of collisions that cause resistance. How could you alter the cross-sectional area of the wire to reduce the resistance? Since the resistance is in the numerator on the left side and the cross-sectional area is in the denominator on the right side, the relationship between these two variables is inverse. To reduce the resistance, we need to increase the cross-sectional area of the wire. A wider wire gives the electrons more room to move and decreases the likelihood that the electron would collide with the atom. If the length of a wire were halved, how would that change the wire's resistance? Since resistance and length are direct, the resistance would be halved. What if the cross-sectional area were doubled? Since the relationship once again is inverse, if the cross-sectional area is doubled, the resistance would be halved. Which plot correctly shows the relationship between resistance and length? The answer is choice 1 because resistance and length have a direct relationship. All of these wires are made of the same material. Rank the resistance in these wires from least to greatest. Looking at the equation, the only thing that's different is the ratio of L to A. And so we find L over A for each choice, and we see that the least resistance is wire 3, and the most resistance is wire 2. To summarize, the resistance in a wire depends directly on the length of that wire and indirectly on the cross-sectional area A.